Okay, so this is an extra lecture that I would like to add it on, and this is topic about activities. And this is you might recall this, I discussed this vapor pressure diagram, and this is a mixture of carbon disulfide and acetone mixtures. And this one is essentially non-ideal solution mixture, which does not obey the relationship. And so let's just focus on the carbon disulfide. Let's say that's a being A. And so this is I guess the mole fraction of an A, carbon disulfide, increasing from 0 to 1. And this is a curve that was provided here. Okay, so this is an experimental result, and this result is essentially partial pressure of A. So for any composition, for example here, that's at a given XA composition, we can measure experimentally and the PA, and then that value is normalized by PA star, which is a partial pressure of carbon disulfide, which is a compound A, at 100% pure composition. So which is actually, that is a value shown up here. So if you just focus on this relationship, this is now, we want to introduce the concept called activity. Before, partial pressure over partial pressure over the pure A pressure was essentially mole fraction of an A. That was an ideal solution. And I told you that this is always true when XA goes to 1, which means A being solvent. Okay? So that is where these things are following. This particular relationship is only true for this tiny little region. But for entire ranges, we want to call this generic concept called activity. And this activity must be related to the mole fraction, and the later people wants to say, and that is activity constant multiplied by mole fraction, so that they can use this relationship as something that is shown up related to the mole fraction. So this is actually this value that you see here is the vapor pressure that is predicted based on the Rao's law, and then this is an overshoot on this. So really the question is, can we predict, and it's in a way partial pressure, and which can be normalized, so the normalized by the ozone vapor pressure as a function of mixture composition. So for example, XA. Can you predict that? The answer is yes. Okay. So here is actually the one of the figure. I'm going to jump ahead and going to show you that this one looks quite similar to something like that, right? This is for the vapor pressure of carbon disulfide as a function of that. So it is it's an example where A and the B are mixtures, and then we want to be able to predict this. And this solution is essentially coming later on. Do you remember the regular solution theory? Where the repulsive interaction is parameterized by this psi. And then this value is a measure of the enthalpy of interaction, which is typically when this is positive, means there's a repulsive interactions, right? And then there is this value is a negative. There's an attractive interaction between A and B interaction. Right? So this is a repulsive. This is attractive. And depending on the levels of the value, and we can fit this the value on top to be able to say, okay, this one is roughly about 1.5 regular solution theory can be described to essentially repulsive levels of repulsive interaction between carbon disulfide and an acetone. As you might recall that when psi value is smaller than 2, the A and B mixtures are miscible. Okay, so and I think that's still acetone and carbon disulfide are mixable, but they can be represented at the levels of, I guess, disfavorable repulsion within this miscible carbon disulfide and acetone, and then we can kind of fit this value shown up here. So I just show you the conclusion of one of the utilities of the concept about activities, and I'm going to show how this thing is going to be figured out. And there is a little small section that I discuss in my the recorded video with a blackboard, and I just wanted to once again trying to explain it to you one more time to give out the more general descriptions. So once again, this one is on A and B mixtures. Throughout, this is A is usually trying to represent here as a solvent, which means the mole fraction of A is close to 1. That's a majority. And so A and B binary mixtures, and the B is a solute. Okay, so that's a minor component. Okay, minor components. The one of the fact that is always true, regardless of the situation here, is the chemical potential of component A. In here, the solvent, which is we call A, from the pure state chemical potential, and the natural log ratio of between PA over PA star. So that has been always true. It is an ideal solution that to reduce this one to the mole fraction. That's only for the ideal solution. But in general, this is a correct statement. Okay, so A is more like a conceptual quantity now, and it is a ratio of what is in the vapor phase and what is supposed to happen when there is 100%. So, this is normally the situation where you have a solution, and this is a vapor phase. So this is a liquid, and there is an A. There's a lot of A. And with an A itself will be a PA star on top in the vapor phase. But now you start to have a little bit of a B, right? So there's a little bit of B. Just imagine that this B and the A has a repulsive interaction. That results in more A's are being tossed to the vapor phase, and then the partial pressure is a measure of how much of the gas is going to come up and come down, and this is a real property as a result of this interaction between A and B, where A is still the majority of the components here. So the A is a real property, and then this real property is normalized by its own pure A vapor pressure, and then that's what we define as an activity. And so this is just on how the experimental measurement can be made here. Okay, so if I and then also A is related to the gamma times XA, so mole fraction and an XA can be related, so that this is some constant that maybe goes in between, and so the gamma and the mole fraction is an activity. And so that's the constant activity constant of the solvent, and it goes defined as shown up here. So because of that, by plugging this value in, you can have this component, and then that component kind of taken out, and this one looks like that is essentially the chemical potential. As if the A behaved like an ideal solution, and then this is a sort of a correction factor. So this is essentially a correction factor to correct and predict or allow to understand the actual chemical potential of an A on here. So what this is simply what they're saying here is this is this value, if you remember that, right? This value itself is a PA star XA. So that's the value that is supposed to be as if they behave like an ideal solution and an A. And then this is an actual PA values, right? So if you're looking at the way that you can do is these two ratio of between these two, that is a PA divided by PA star XA. So what's that going to be? And that will be essentially activity of A divided by mole fraction of an A. So the ratio between these two values will be essentially gamma A. So right. So therefore, when this value on top is same as the ideal value, the gamma A will be 1. And if it is when gamma A is bigger than 1, then means the PA is bigger than PA star XA. That's the value supposed to be, but it is bigger, is a positive deviation, which is where we've shown it here in the carbon disulfide case. So okay, so this chapter is essentially trying to compare and then give you out the general idea. Okay, so this is what is known as for given that A is a solvent, and this is how chemical potential of an A in a mixture, right? In a mixtures of A and B, right? And so then they are talking about they're giving this definition, and then they're trying to see bring out some common comparison of these two. So the next section is they're going to talk about the solute activity. So solute here is always a B, and that is a minor component. And then as you remember the diagram that I shown in a beaker, there is a lot of A. A is a majority component, but there are minor component of the B, which is experiencing this interaction between neighbors. It could be A or it could be actually B itself, but as a result, some B's are ended up being on the vapor phase, right? So this is some B's are ended up being in the vapor phase, and what we need to record is, okay, so what about the vapor pressure of B itself, right? That can be a measure, and then compare that to what's the value that is in the pure state. So this is how much of the activity compared to the vapor pressure as if they are 100%. So we can think about to define this one to be the way that how it is to be. So this is really always a case. Vapor pressure is so on that whether it's an A or a B, this is how the real relationship is going to be the relationship between the activity and the vapor pressure of the system. So this is always true, but now we are going to put a case where things are behaving as if they satisfy the Henry's law, or if they does not behave the Henry's law, and then eventually we'll have a very generic expression that give you to the next section of the discussion. So once again, remember that, right? Whether it's an A or a B, this is essentially is a defined activity. The vapor pressure in the mixed state compared to the pure state, That's how their activities in the mixed state. So that's this one. But in the case of number one, which is what they call the ideal dilute solution, because of the solute B satisfy the Henry's law, and when they find the Henry's law, the vapor pressure in the mixed phase now can be described in relationship with a mole fraction of the solute, but now the constant is proportional constant is Henry's constant. Okay, so now we can put this Henry's law equation shown up here, and now I have this new relationship. But now I'm just trying to crank out the portion that is essentially a constant, right? Okay, so I'm essentially what I do is I'm taking this portion out and then keep these other portions in like this. So by doing so, what you see here is a chemical potential of solute is now, and they going to put a different notation, chemical potential of B of a standard state. So this is a pure is a standard state for the solvent, and we do not have those luxury of calling this is a pure state. We're just going to say is a solute, and we just call it as standard state. What I call whatever that means, right? So it is essentially the A term that is corresponding to the chemical potential, and then RT ln XB. So when I say whatever that means it is essentially when XB goes to, this is really the case, XB is essentially likes to be a zero value, which is a solute. And this one is cannot, the reference point is cannot be found from the pure state of a B, but it is actually more related to the combination of Henry's constant and so on. So this is a conceptually, there is a state, which is serving as a more constant value state, and then they still retain this proportion, functional group relationship between the activity of a solute is a natural log of the mole fraction of solute. You just have a different standard state, which is not as conceptually easy to understand, but formula-wise, you will find an awful similarity. Right? This is a solute. That is a state. Okay. Okay. I think actually what I meant to say was. Let me actually delete this, right? So let me delete that, and this one, what I meant to say is that will be an XA, right? And then this is trying to relate this to, and that is a pure state, and this is a case where, wow, that's the case where Raoult's law applies, where this is a Henry's law applies in this pairs. But generically now we are going to modify those two equations, that is the following this, to a much more generic relationship, which is shown up here, but I'm going to write down once more to just want to make sure. So what that means is generically the mu A is now mu A star plus RT natural log activities of an A, and the mu B is a mu B not a standard plus RT activity natural log of an activity. Okay, so that's how those more general, right? So general relationship, you can start to have this concept, because once again because of the B is a solute, we are essentially choosing activity in place of what used to be a mole fraction shown up here in the previous case, and we just have to accept that we cannot use the pure state as my reference state, but just something that there is a standard state that is corresponding to do that. And that was something that I was trying to explain in my Blackboard lectures, and that was really the key point of what I want to say about that. Okay, so now I want to continue a little bit so to show you the third section, which is okay, so if it is a solute, and then sometimes people have a different ways of describing the concentration of a solute, and mole fraction may not be the common choice. Sometimes they just call it a molarities, and then in place of a mole fraction. Okay, so it is a proportional constant that is related to the mole fraction of a B. So whatever this the constant that they're going to put it in will be represented. So this relationship can be also used. So all of a sudden that the concept about activity, the chemical constant is chemical constant of a standard state, and in the mixed state, we are talking about the solute activities, and then this activities is related to not only the XB, but it is also we can choose to use this sort of the rate of molarity divided by standard state, and then that is just 1 mole per kilogram, so which is a dimensional quantity on here. So what I'm trying to say is this relationship between in the standard state and the solute, and then that's the chemical potential as in the mixture for the solute, still retain this the kind of the function relationship is shown up here. Okay, so that's general one. So the final one that I want to talk about the activities on the which is related to the regular solution, and that is actually related to the one that I discussed in the beginning of this the recordings. So do you remember that the delta G mix can be described by this entropy of mixing, and then this is the enthalpy component of the mixing, and so that's how the regular solution delta G mix can be described. But now we are going to be a little bit more generic in here, saying that okay, so the mole fraction here is that is true, but in a way that delta G mix can be described by this. This is essentially what is called the activities, right? So this is an activity A, and this is an activity B. So delta G mix can be described by these two factors, and then by putting these two together, which is you can get this XLN A, XLN B, and these are the components that it has something to do with interaction of these two material, A and B, and then that must be related to those two. Okay, so I kind of skip this skip the math on the one and trying to give you a focus on this is activity constant coefficient A is actually related to the mole fraction of the B. So ln gamma A is actually psi 1 minus xa to the square. So this is what is called the Margulis equation, and then the ln gamma B is psi 1 minus xb square. Okay, so these are the relationship that is give rise to, and then all of a sudden that we start to have a better understanding about this constant related to the activity, and which is a ratio. Do you remember that? For example, the gamma A was what? PA, and divide by PA star times XA. So that's the value is supposed to be. So by doing so, what I can do is, now I do have a, this one is now psi 1 minus, actually, okay, so what I need to do is 1 minus xa to the square, but that is ln psi, right? So by doing so, this equation on top is going to be PA over PA star mole fraction of an A is an exponential psi 1 minus xa to the square, and then that's what you see here. Okay, that's what you see. So now I can predict this PA values being here, which is a PA star and mole fraction of xa and this value. Okay, so this is the one that I shown you before. That is a mole fraction of an A when A and B has this sort of the enthalpy of interaction parameter called the interaction parameter called psi. Within the mixtures, what is the vapor pressure of an A on top, right? And if the psi value is a positive, A and B has a repulsive interaction. If psi has a negative, greater than 0, psi is a negative, A and B has an attractive interaction. So I can anticipate that in this case where psi value is lower than 0 than 1, actually the A likes to stick to the B, so there's a less vapor pressure that developed, and whereas the psi value is positive, which is more common here. And that's the case of where they have a positive deviation, something like that, depending on how much height they are. And this is essentially a deviation from the value is supposed to be when there is no difference in interaction between A and B and A interaction. Okay, and so that's what the value should be. And so this is actually turns out to be very useful. So, for example, this is think about, I'm having a mixture of benzene and so cyclohexane, and then the interaction parameter is actually generalized with this interaction parameter psi at the number of 1.13. So that's the levels of interactions. And then I can essentially use PA, okay, and if A is a benzene, and then that is a PA star, XA, E, psi, 1 minus XA to the square. So that's the vapor pressure of, essentially pressure of a benzene. And then this is a vapor pressure of the cyclohexane. Okay, so if you look at that, benzene versus the cyclohexane, one is aromatic, the other is aliphatic, and benzene, I'm sure benzene likes each other more than when they interact with the benzene and the cyclohexane. So therefore, there is a little bit more penalty for benzene is experiencing it. So does this, because of this similarity between the cyclohexane and the benzene. So cyclohexane likes their interaction, but this AB interaction causing these levels of interaction parameter caused by the chi. So that's why this value can be predicted once again. That is the value that is supposed to happen as if the Rao's law, ideal solution law, can happen. And this is an actual value. And then we were able, I think the people were able to kind of fit this one with an interaction psi value at 1 point, what was the value? 1.13. And then that was really the way that we can have some better understanding on this. Okay, so this is a case once again. I mean, as a project that, in the regular solution theory, we can kind of find out what will be the value that is close to do this, to describe it, and we can try to figure out what will be the value for that. And so I'm going to make some actually project for you to compute and the interaction parameter for the psi, given that this is a carbon disulfide the case. Okay, so thanks for your attention. And then actually I also want to give you a head up on that there's another activity section in the one, and this is what is called the Debye-Hoco theory. I know that there's a lot of students taking from the PChem for life science, and the life science physical chemistry system, typically in the aqueous solution system where there's a lot of ions inside in a lot of biological system or biochemical system. So understanding the activities of the ion is very important, and I'm going to record a separate section for that to complete this essential section 5F of the activities. Okay, thank you for your attention.